The resolving power of a telescope. See, the resolving power for a telescope, this is a very, very important point, because see, the objects whatever we are looking at will be very, very far, correct? It could be like thousands or millions of light years, or even if it's a terrestrial object, it will be like few kilometers, correct? Now, so when we say the resolving power of a telescope, so usually we consider for an astronomical telescope. See here, one thing is, if you are looking at, let's say, a binary star, okay, two stars which are very close to each other, then we actually need to figure out that those are two stars, not just one star, right? See, a very famous example is there is a star called Sirius. So this is a binary star. Up until like 50 years, we didn't know that it's a binary star. We thought it's a one star. So as the technology improved, we figured that it's a binary star system. So for this, to resolve that it's two stars, like binary star, important thing here is the angular resolving power. It's not the linear one. Okay, so we have theta is equal to lambda divided by d. So as you see in the figure, see, that is theta, lambda is the light, and d is the aperture of the lens. Okay, so as we have this, see, the aperture is circular, correct? So we get theta is equal to 1.22 lambda divided by d. Okay, so this is basically theta. Okay, or what we can say, it's the limit of angular resolution of the telescope. Okay, to find the resolving power, we need to invert it. So we have 1 by theta is equal to d divided by 1.22 lambda. Okay, this is the resolving power of a telescope. Now, resolving power depends on the size of the aperture. More the value of d, more the resolving power. This is the reason we see huge telescopes. Like the aperture will be few meters. Okay, the size of the lens will be few meters. So except that we actually don't have glass lenses, we use different types of telescopes. Having a glass lens of 2 meters, the aperture is extremely hard. Okay, then it is inversely proportional to lambda. But here what we have is, see, we cannot control lambda here, correct? The light ray is coming from a very far distance. So lambda could not be controlled, but d value we can change. This is the reason telescopes have very, very big apertures. Okay, but whereas we can use different types of telescopes to figure out the lambda. Like instead of having an optical telescope, we can have infrared telescope, or we can have an ultraviolet telescope or an X-ray telescope, where lambda value will change. So if lambda changes, then resolving power will also change, correct? So by using this formula, which is d by 1.22 lambda, we figure out what has to be the aperture of the lens, or what type of telescope we have to do, like either UV or optical or X-ray or whatever. Then we can figure out the resolving power of a telescope.